However, this is Haifeng from Peking University. Today is my pleasure to be here presenting our work, AutoSketch. In this paper, we focus on the network telemetry, which is significant to network management, since many management tasks, such as performance analysis, fault diagnosis, and anomaly detection, rely on the traffic statistics provided by underlying telemetry systems or algorithms to make the management decisions. In recent years, sketch-based algorithms are very popular in the field of telemetry algorithms due to their memory efficiency and the controllable measurement accuracy. Especially, the development of programmable network technology has enabled sketch algorithms to be deployed in network devices, leading to a surge in research works. However, it is non-trivial for network operators to deploy them in practice. Here, we summarize 3 user burdens. First, for different types of measurement tasks, there are diverse sketch algorithms. As a result, users have to select the appropriate algorithm for each measurement task. The second challenge is how to config these sketch algorithms. The theoretical error bounds of existing sketch algorithms usually show worst-case results, which is not efficient for practical deployment. Lastly, realizing sketch algorithms on programmable switches is also very challenging. Users need to use unfamiliar programming languages and consider various hardware constraints. Conversely, another class of telemetry research works, that is, query-driven network telemetry, aims to reduce these user burdens as much as possible. They usually provide expressive telemetry languages, allowing users to focus on the query logic. Taking Sonata, which was published at SIGCOMM 18 as an example, it automatically divides measurement tasks between the programmable switches and the end hosts, hiding the underlying implementation details from the users. Our work, AutoSketch, aims to eliminate the aforementioned user burdens of selecting, configuring, and implementing sketch algorithms. We combine the advantages of both query-driven telemetry and sketch-based algorithms. That is, users can determine measurement tasks using familiar operators like MapReduce. Then AutoSketch will automatically compile the query into the sketch program implemented in P4, facilitating the deployment on programmable switches. In this way, AutoSketch can achieve strong expressiveness, resource efficiency, and controllable measurement accuracy at the same time. AutoSketch faces 3 challenges to combine the strengths of both sketch algorithms and query-driven telemetry systems. First, since sketch algorithms incur errors due to their approximation nature, users need to be able to perceive and control these errors. To achieve this, AutoSketch extends the data stream abstraction with the accuracy intent interface. That is, the interface of AutoSketch includes 2 parts. For the first part, we adopt the data stream abstraction as its telemetry language, because the data stream abstraction is expressive enough to cover numerous queries and is widely utilized by many query-driven telemetry systems, such as Maple, Sonata. Here, AutoSketch provides 5 common built-in operators, including map, filter, distinct, reduce, and zip. As shown in this figure, we can define a DDoS detection task using only 8 lines of code. We also provide a group by operator, which allows user-defined functions to track some non-summable flow-level state, such as a timestamp and TCP sequence number. Here, we use a group by operator to define a TCP non-monotonic task, which counts the number of packets per connection with sequence numbers lower than the maximum so far. For the second part, we propose the accuracy intent interface, which allows users to specify an acceptable error bound for the query when defining the measurement task. Currently, we support 4 accuracy metrics: recall, precision, average relative error, and confidence. As shown in this figure, users expect that in 99% of cases, the DDoS detection can achieve at least 95% recall and precision. It is worth noting that the accuracy intent is the key of AutoSketch. It guides the selection and configuration of the underlying sketch algorithms. The second challenge is how to map diverse telemetry queries into appropriate sketch algorithms. To address this, AutoSketch takes operator-level sketch mapping. That is to say, we map each stateful operator into one sketch instance. This figure shows one possible mapping for the DDoS detection task. We map the distinct operator into a Broom filter and a reduced operator into a counting sketch. Here, we choose the operator level mapping instead of query level mapping because it can achieve better generality and flexibility. Although we can map the complete query into one general purpose sketch algorithm to ensure generality. However, the range of query tasks supported by existing universal sketch algorithms is still limited. In particular, they cannot cover some user-defined operators. For flexibility, operator-level sketch mapping allows fine-grained sketch selection and tuning. However, most existing universal sketch algorithms are usually composed of multiple basic structures whose overall resource usage is non-trivial and hard to be optimized. Here, AutoSketch adopts the key value separation storage mechanism from our previous work, OmniWindow, which was published at SIGCOMM 23, to maintain the new flow. We use this mechanism to maintain the new flow keys in a flow key buffer. Thus, we can focus on how to use different sketch algorithms to maintain various flow values. We take different sketch mapping strategies for user-defined and built-in stateful operators, respectively. Here, for user-defined operators, we propose a sketch-like structure to maintain the user-defined states. It is a two-dimensional matrix. To process a packed tuple, we hash its key to one cell in each row, and then invoke the user-defined function to update the states in the hashed cells. When querying for the key, we use the same hash functions to select the cells and aggregate the cells based on the monotonicity of the state and to mitigate the errors caused by hash conflicts. However, a group by operator may contain multiple states. For example, this group by of TCP non-monotonic contains two states, max sequence so far and the NM count. If we map such a group by operator into one sketch-like structure, multi-state updates may exceed hardware capacities, which is also hard to tune memory resources for different states. To address this question, AutoSketch proposes the AST-based operator decomposition to achieve one state, one group by. Thus, we can construct one sketch-like structure for each decomposed state. This figure illustrates the operator decomposition process of this group by operator in the TCP non-monotonic task. Here please see our paper for more details about the decomposition algorithm. We can see that after the operator decomposition, we have partitioned the two states max sequence and NM count to two separate group by operator. And for built-in operators, since their functions are fixed and common, the difficulty of sketch mapping comes from the fact that many classical sketch algorithms can implement them. For example, we can map the distinct operator into Broom filter or counting Broom filter. We can map the reduced operator into a counting sketch or count sketch and more algorithms. Since these algorithms achieve different levels of resource accuracy trade-offs, to determine the appropriate sketch algorithm, AutoSketch utilizes sampling-based sketch selection for built-in operators. We include it as part of the initial phase of our AutoSketch configuration approach, which will be introduced next. The last challenge is how to configure these mapped sketch algorithms. Here, AutoSketch adopts a benchmark-based sketch configuration approach. Ideally, we aim to convert the user-declared accuracy intent into error bounds of the sketch algorithms. Then, based on the theoretical analysis of sketch errors, we can determine the appropriate type and configuration of sketch. However, it is still an open issue to integrate the errors of multiple heterogeneous sketches to firm query level accuracy. In addition, as mentioned above, Existing sketch algorithms typically address worst-case scenarios, thereby providing limited guidelines for parameter tuning. Instead, we adopt a bottom-up approach, enumerating all possible sketch configurations and benchmark each one with network traffic. This allows us to select the configuration that can meet the user's accuracy intent with a minimal resource usage. Here, we design an efficient searching algorithm with many optimizations to accelerate the searching procedure. One is LHS-based initialization, which can simultaneously determine the sketch type of built-in operators. And another most important optimization is hardware-aware configuration generation and proving. We put more details about these searching algorithms in our paper. Here, we prototype AutoSketch top inter-orthogonal switch. We realized 11 telemetry queries and compare AutoSketch with 2 state-of-the-art query-driven telemetry systems and 8 classical sketch algorithms. We evaluate 2 accuracy intents for the queries. Here, we show the comparison results with sketch-based telemetry algorithms. We test 3 classical queries that have been extensively studied by sketch algorithms: heavy hitter, superspreader, and cardinality. We evaluate 2 specified sketches for each query and 2 universal sketch algorithms for all the queries. As shown in the figures, we can see that AutoSketch consumes much lower switch resource usage than classical sketch algorithms. As previously explained, this is because the theoretical error bounds of existing sketch algorithms usually address the worst-case scenarios, which is not efficient for practical deployment. Note that configuring these classical sketch algorithms theoretically requires some domain knowledge, which is not easy. However, using our AutoSketch needs no effort to tune these parameters. For the controllable accuracy, AutoSketch can satisfy all the accuracy intent for all the telemetry queries. However, some other sketch algorithms cannot meet these accuracy intents. This is because the desired resources of some complex sketch algorithms exceeds the hardware capacity, and some others are too sensitive to the harsh conflicts. We provide more results in our paper, including the comparison with query-driven telemetry on the switch resource overhead, bandwidth, and query accuracy. We also put more results about the parameter tuning, searching cost, and the efficiency of our searching results. Here, AutoSketch is a framework that can be further extended. We are currently engaged in the following aspects, including the support for multiple query and distributed deployment, more backends such as SmartNIC and DPDK. We also try to support more sketch algorithms by designing new sketch-like structures for the group by operator, adding new sketch candidates for existing operators, and introducing new operators. AutoSketch can also be integrated with many emergent sketch optimization techniques, such as BitSense, SketchLab, or New Window. In conclusion, AutoSketch combines the strengths of both sketch algorithms and the query-driven telemetry systems. It achieves strong expressiveness, resource efficiency, and controllable accuracy. The key components include the accuracy intent interface, operator-level sketch mapping, and the benchmark-based sketch configuration. The source code of AutoSketch is now available on GitHub. Thanks for listening. Now, I'm happy to any questions.